study by McKinsey found that 8 out of 10 construction projects finished late. These were all major construction projects with experienced project managers and planners. So given this, why do so many construction projects get delayed? Do clients set unrealistic finish dates? Do planners get the methodology wrong? And do the construction teams ignore the plan as soon as they start building? Well, yes, all these factors probably contribute, but the reality is project scheduling is super difficult. To build a good project schedule, you need to understand the project scope and the quantities of work. You need to plan the construction methodology and sequence it logically. You need to define task dependencies correctly, and you need to factor in resourcing across different tasks. Then, to manage the schedule during the construction phase, you need to communicate and constantly refine the plan. You need to track progress against the baseline correctly. You need to predict issues before they become problems, and you need to adjust for delays, clashes, and resourcing issues. So in this video, we're going to teach you exactly how to do that. We're going to teach you construction project scheduling. We'll cover what is scheduling and how it's actually used on projects, why scheduling matters and how it makes contractors more money, the core scheduling concepts. Then we're going to cover in detail the core stages of construction scheduling and the one that everybody ignores. And then we're going to finish with some pro tips and mistakes to avoid. This is the exact scheduling system I use. It's a blend of boring, critical parts scheduling, but also the best parts of lean construction and agile scheduling. Whether you're a business owner, project manager, or project engineer, these techniques will work for you. And if you want to get the slides, I'll put a link to download them in the video description. Before we dive too much into the content, we need to address the important question of how is scheduling actually used on projects. If you take any project management course or go through any project management textbook, they're going to tell you that scheduling is the most important skill. You need a 10,000 line Gantt chart to deliver a project. But the reality is that's just not how things happen on real world construction projects. This is what we actually see happen. Starts with a client setting some unrealistic finish date. They say they want the project completed in the next 12 months. They then go to market. 3 to 6 contractors quote to deliver the project. The most aggressive contractor, the one who's desperate to win the job, will say, yep, we can meet that. They reverse engineer the schedule and they come up with some completely unrealistic baseline schedule. They submit this schedule, they sign a contract saying that they'll meet the client's finish date. As soon as construction starts, the schedule becomes a reporting tool only. It's a tick and flick exercise and it doesn't reflect how the job's actually being built. The actual decisions on site are driven by instinct, deadlines, and chaos. That finish date remains fixed, so the team throws money and resources at it to meet their contract completion date. Extensions of time claims are made and argued with pretty poor substantiation. Now, I'm not saying that this happens on every single project. Sure, some projects implement scheduling beautifully, but most projects I've worked on, this tends to be the pattern you see, which leads me into the dirty secret of scheduling. You don't actually need a schedule to deliver a project. You need a contract, you need an estimate, you need quality assurance and compliance certifications, but the reality is you can deliver a project without a schedule. Lots of experienced construction project managers effectively run the job in their head. They know the methodology, they know the constraints, they know the resources, and they work backwards almost from their gut feel. And the reality is a lot of experienced construction managers actually do a fantastic job of this. I call it scheduling without schedules. Experienced project managers can visualize the full build sequence, the key constraints for risks, and the resourcings they need week to week. They don't need Primavera or Microsoft Project to tell them this, but the problem is tends to only work from there. So what's wrong with this approach? Well, it tends to fall over with scale. It does not scale with complexity, team size, and it's hard to delegate to other team members. Leads to missed tasks and clashes, mistakes, the inability to substantiate claims like EOT claims, frustrated stakeholders, and poor forecasting. So yes, experienced construction managers can run a lot of things in their head or using their own methodology, but the best project managers know how to use scheduling effectively. Okay, this leads on to my next point, which is why scheduling matters and how does it make contractors more money. So the number one reason is that it just gives you planning clarity. The best schedules take gut feel, experience, the knowledge of the most experienced construction managers and turn it into a plan that everyone understands and can follow. It's a famous quote by Dwight D. Eisenhower that plans are useless, but planning is essential. And it captures this idea that a plan that everyone can see, everyone agrees on, helps to identify clashes, identify constraints, optimize the sequence of the build, and gives you smoother delivery. Better plans mean fewer mistakes, rework, and changes. As an extension to this, it helps with communication and delegation. The schedule becomes the source of truth. There's a clear plan that shows who needs to be where and when. It aligns the project team, subcontractors, and suppliers with the baseline. The schedule is the source of truth. It helps answer questions like, when do I need to be on site? How long do I need to allow for material procurement? And this is all captured in the project methodology, and it helps to communicate this to everyone who needs to work. So scheduling helps with coordinating, delivering the project. It's also a fundamental part of construction contract management, particularly with negotiating and getting claims approved. Contracts typically require contractors to maintain a program. So you have your tender baseline program you initially created, then weekly, fortnightly, monthly, whatever the contract says, you'll need to report on your progress against this program. Doing so will help you keep your client happy, but it will also help you be protected from liquidated damages by helping you to substantiate any EOT and delay claims. If you've got a program, it shows everything your client was meant to provide you. Maybe they were meant to approve the design by a certain date. If they're missing these dates, it's incredibly easy to claim delays and protect yourself from liquidated damages, but also easier to claim additional costs if you've been fairly delayed. Without a program, it's almost impossible to claim these things. Now, a good schedule also helps you to manage the project stakeholders. I've already talked about the benefits of communication by having a source of truth in the schedule, but it also keeps your client and other key stakeholders happy, makes you look professional, makes you look like you know what you're doing, and it also helps to set realistic expectations and timelines for when the project will be completed. It's an easy way to report on progress. It's an easy as a basis for progress meetings, and it's going to help reduce disputes because everyone can see the plan, everyone can see the methodology. Again, there's a source of truth for everyone to agree on. Next, scheduling helps you save money. So helps you to optimize with smart resourcing, such as avoiding downtime, having multiple mobilizations from subcontractors, clashes between work groups. Also helps you to better plan your methodology. It helps to inform decisions like whether to self-perform works or subcontract them. For example, if you have a long continuous run of work, it might be better to set up your own self-perform team. But if you have big peaks where you need a lot of work done and then downtime, it's going to be better to subcontract. You can use that same principle for whether you hire in plant or whether you've got consistent use of plant throughout the duration of the project. So you might choose to buy it and then sell it at the end of the job. Scheduling helps you really optimize your costs and come up with the best methodology, and also just leads to less chaos and fewer cost blowouts. Okay, so instead of just boosting your profitability by reducing your cost, scheduling also helps a lot with managing your cash flow. It helps you to align your payment claims with progress. It can be used to actually substantiate payment claims. It can also be used to forecast material and labor costs more accurately, so you know when you're going to be spending money in the future, so you can manage your cash in your bank. And it also helps you to avoid over ordering materials or delayed deliveries, which can again impact your cash flow. More predictable cash flow, as any contractor knows, is essential to keeping a business running. Look, in a lot of ways, scheduling can be a competitive advantage for your business because a lot of contractors just don't do a very good job at it. It's going to help you finish early, which is going to help you save money with higher margins. It's going to help you to consistently deliver, which is going to make you look better to your clients, so actually get you more work in the future because it demonstrates your professionalism, and it's also going to give you confidence to scale. Okay, just to answer this question, how does scheduling make contractors more money? How does it maximize their profits? On the revenue side, it's going to help you to deliver faster and to get paid what you're owed if your client delays you, and avoid penalties and lost income by being able to claim for delays. It's also going to help you to limit your costs. It's going to help you to plan more efficiently, reduce waste, come up with the optimal methodology, optimize your resources, but also reduce your indirect costs. So if you finish the project faster, you're going to be paying less staff salaries, hire of equipment, hire of temporary office buildings. So you can see on both sides, the revenue and the cost side, scheduling has a range of benefits. So now we understand why we should schedule. Let's get into the guts of the technical side of the topic and begin by answering the question, what actually is construction scheduling? Okay, so put simply, scheduling is just planning and managing when each part of the project happens. It's taking all the tasks and saying when each task needs to happen, what needs to happen before and what can happen after. The process and tools we use to manage time. So there's two key things the schedule captures. It captures how the work's going to be delivered and when it's going to be delivered. So how is the methodology we're using to deliver our project? So it captures both mandatory linkages. For example, we need to order materials before we install them, but also discretionary linkages. So for example, do we want to use 10 crews to do this, or do we want to use one crew and do it slowly? So that's the how, our methodology. And based on this, it captures the when. So for every task we need to do to complete our project, when is this activity going to happen? What's the planned start and finish date? What are the linkages? What needs to happen before? What can happen after? And what is the duration? The output of this is the schedule. 9 times out of 10, it's going to be a Gantt chart. A Gantt chart is simply, as you can see on the screen, a list of activities, their duration, their planned start and finish dates, and then each activity is represented as a bar. So the bar shows when the activity starts, when it finishes. Then there's lines drawn between the activities which show the relationships to the following activities. So the Gantt chart is the document that captures our schedule. The construction schedule lists all of the tasks, the activities we need to complete our project. It shows the start and finish date of each task. It maps the dependencies between the tasks. So what has to happen before, what can happen after. It highlights milestones, any critical deadlines. For example, our contract commencement date, our contract completion date, any milestones we have along the way. And it also identifies the critical path. So that is the series of activities within our schedule. We'll explain this more later, but that if get delayed, delay project completion. These are the series of tasks that determine our project's finish date. The schedule is then the plan that's followed during construction. So we develop it during the planning phase. It's then our baseline for what we follow as we deliver the project. We refer to this as the baseline schedule. We update it during delivery, and we also derive from it a whole lot of sub-schedules that we use during construction. For example, construction teams usually have some sort of 3 to 6 week look ahead that they use to plan and coordinate the day-to-day construction activities. The procurement team might have a separate procurement schedule that shows all the packages, when they need to be awarded, when the materials are needed on site, and we'll have some sort of daily plan. So all of these are sub-schedules that get derived from the master project schedule, the baseline schedule. Okay, so now you understand the idea of a schedule and the baseline schedule. Let's talk about some core scheduling concepts you need to understand. So the first one is an activity or a task, which is the base unit in the schedule. We have a list of tasks, a list of activities like placing formwork, steel fixing, pouring concrete that we need to complete the construction work. Each task needs to have the following attributes. It needs to have a start date and a finish date. It needs to have a duration, and it needs to have dependencies. So every task will have work that needs to be done before and work that needs to be done after. We also have milestones. So milestones are 0 duration events that mark key achievements. For example, you might have one for contract award, foundations complete, handover of the entire project. These are the deadlines that drive progress. These are the fixed dates that our stakeholders, our clients, these are the dates everybody cares about and the dates that everybody's working towards. So people usually don't focus too much on tasks. They set their finish dates, and these are the dates that actually drive progress. The duration of an activity is the time an activity takes to complete. This is going to be based on things like the quantity of work you have to do. For example, if you have to do 100 meters of trenching versus 1,000 meters of trenching, the productivity, so whether you can do 50 meters a day or whether you can only do 20 meters a day, and the number of resources, whether you're going to use 10 crews or whether you're going to use 2 crews. key concept with an activity duration is whether you have a production-based duration, which means it's purely based on the number of resources you apply to it, or a program-based duration. So some activities have fixed durations no matter what. For example, if you order steel reinforcement, it might have a 4-week lead time, or if you order an electrical transformer, it might have a 70-week lead time. These are referred to as program-based durations. Now, resources are always a contentious issue when we talk about scheduling because it can add a lot of confusion to a schedule, but a proper construction project schedule is resourced. What this means is that there's the assignment of labor, plant, and materials to a task. For example, our trenching activity might have an excavator, an operator, and a spotter assigned to it. What this does is it helps to align the estimate with the schedule, but it also helps you to understand the relationship between tasks based on your available resources. This is a really core concept in scheduling and something that makes scheduling very complicated. You can level resources or you can smooth resources. So leveling resources means you're avoiding overloading resources depending on the number of crews you have. For example, if you only have one crew and you've got all these tasks occurring at the same period of time, you would need to level your resources because you've only got availability of one crew. It's going to push out the durations of these activities. Smoothing, on the other hand, is where you spread work without extending project time. So you optimize the usage of your resources to avoid delays. Okay, so you can see an easy visual explaining this. But say, for example, you can only work 45 hours a week, and there's all these tasks that come out of the schedule. In the first week, there's 60 hours of work, but in the 6th week, there's only 10 hours of work. Resource leveling is saying that we can only work a maximum of 45 hours a week. So we have to take some of these tasks where we've got more than 45 hours per week. We need to move them from week 1 into week 2, from week 2 into week 3. What this does is it pushes the duration of the project from week 7 to week 9. Resource smoothing, on the other hand, is without violating that constraint of 45 hours of work per week. It's taking the ups and the downs and it's turning into a consistent 38 hours per week. Next, the critical path. And I would say this is one of the most misunderstood terms in construction project scheduling. Critical path is the series of tasks that, if delayed, delay project completion. It's the longest path of dependent tasks. Controls the earliest possible finish date of the schedule. And if you can delay the task without impacting the finish date, by definition, it's not on the critical path. And the other thing you need to understand is this isn't a scientific set in stone term. Often when we look at a schedule and something has, say you're talking about a 12-month project and it has 2 days float, yes, theoretically, it's not on the critical path, but practically it is. No schedule is accurate down to the day. So the idea that something has 2 days float means it's on the critical path. The other really important thing you need to understand is the critical path is dependent on resourcing. You can have critical path activities that are program driven. So there's nothing you can do about the duration of the task. That's different to a critical path activity where we can adjust the resourcing and do it faster. So these are some of the things you have to keep in mind. And it's some of the things you have to understand when you're looking at a schedule. And it's where it really scheduling becomes as much as an art as a science to understand the data that's driving these program durations. When we talk about optimizing the schedule, trying to bring forward the completion date, the only way to do this is by reducing the critical path, working out how we can take tasks on the critical path and make them shorter. Okay, so if you look at a really simple Gantt chart, you can quite easily visualize on this what is a critical path task and what's not. For example, site preparation. If site preparation gets delayed, it pushes all the in-ground services back. Therefore, it's on the critical path. If we delay site preparation by a week, it's pushing out our finish date. If you look at the next set of tasks, the in-ground services, you can see that the power in-ground services, if they get pushed back, they're going to push back excavation. But water services, on the other hand, or the data services, we could push those back a week or two. It's not going to push back the excavation activity. So those activities are not on the critical path. They have some float associated with them. But if you do delay them enough, they will start pushing back the next activity, which is where we're going to talk about float. Okay, so float is basically how much you can delay an activity before it impacts your critical path. Total float is your impact, how much you can delay an activity before it impacts the critical path. Free float is how much you can delay an activity without it affecting the next task. The difference between these two is if your next activity is on the critical path, your total float will be equal to your free float. If you delay the next activity, you're delaying a critical path activity. But if you delay an activity that's not on the critical path, then you have some free float. Okay, next we have constraints. A constraint is any limit or restriction that affects how and when activities can be carried out in a project schedule. You can have a time constraint, for example, a deadline, a fixed start or a fixed finish date that you have to work around. You can have resource constraints. For example, you might have limited access to labor, plant, or materials. You might have a physical constraint. For example, due to site access, you can only have one entry in and out, which might impact how your deliveries go. Or you might have a certain number of days that it's raining where you can't work. Or you could have a contractual constraint, which might be some fixed contract completion date. So all of these are restrictions of how and when activities can be performed. Okay, next we've got the idea of schedule optimization, which I brought up when we were talking about the critical path. But this is how we reduce the duration of the project by optimizing the schedule. By definition, the only way we can do this is by reducing the critical path. The critical path, the longest series of activities that we need to complete the project, we have to reduce the length of the critical path to reduce the length of the project. There's two ways we can do this. We can fast track activities, which is, if you look in the diagram, that's where we overlap tasks. This adds risk because you introduce the risk that if task 1 has to be completed before task 2 can start, but you want to bring them forward, so you overlap the activities, there's more of a risk that task 2 will get delayed because they'll run out of work to do because task 1's not complete. The other way we can accelerate the schedule is with crashing. So this is adding resources to accelerate progress, which adds cost to the project because you're adding more people, they're going to be working less effectively, you have to pay for more inductions, you have to pay for more onboarding. Generally, adding resources will increase the cost of the project. Okay, next we've got activity linkages. The linkages between tasks define the workflow or the methodology. For example, we need to do the excavation, then we can start the concrete works. We need to install the underground conduits before we can start pulling cables. The task linkages capture the methodology, how we're going to build the job. Key types of task linkages are mandatory, so things that have to be done in sequence. For example, you need to order materials before you install them, or you can have discretionary linkages. So these are choices in the way we do the work. Classic example is resourcing. We can have 10 crews or we can have 1 crew. That's a choice we're making, and that captures our methodology and how we're proposing to build the project. Okay, so there's 4 main types of activity linkages we can have. The classic is the finish to start relationship. Activity A has to finish before activity B can start. We can have a start to start relationship. Activity A and activity B need to start together. Or we can have a finish to finish relationship. For activity B to finish, activity A must finish. Or we can have least common, which always confuses me. And every time I see an example of, I get slightly confused, but it's a start to finish relationship. For activity B to finish, activity A must start. Okay, so I'm going to give you some more concrete examples of these to help you better understand. So the finish to start relationship is the most common one, which is task B cannot start until task A finishes. For example, task A might be pouring concrete. Task B might be structural framing. You need to finish the concrete foundations before you can stand the frames on them. That's a classic example, and that'll be 95% of the activities in our schedule. The next type is a start-to-start relationship. Task B cannot start until task A starts. For example, when you start excavating, so say you're digging like quite deep foundations, you can start the shoring at the same time. So as you dig down, you put the shoring around the walls. So as soon as excavation starts, shoring can begin in parallel. So these activities would typically have a lag between them. They wouldn't start exactly the same time. You might start with 2 or 3 days lag. The next type is a finish to finish. So task B cannot finish until task A finishes. For example, if task A is installing a ceiling grid and task B is installing the tiles, for the ceiling to be complete, both Both tasks must finish at the same time. And by far the most confusing one is start to finish relationship. So task B cannot finish until task A starts. So say the only good example of this I've seen is that say you're decommissioning an old power system. So task A is to start your new switchboard. Task B is to decommission your existing switchboard. You can't turn off the old system until the new one comes online. Again, there's this key concept of mandatory versus discretionary linkages. And this is really important to understand when you're creating your schedule, because one of the biggest mistakes I see people make is they put in a whole lot of discretionary linkages and their schedule becomes too complicated too fast. A mandatory link is something that must be carried out in order. For example, you can only complete the concrete pour once the foundation is excavated. It is physically impossible to do it any other way. Discretionary linkage is where tasks are sequenced to save money, optimize resources, or other benefits. For example, you might choose to use less resources and extend the duration of the project because you want to use less supervision. So that's an example of a discretionary linkage. Now, you can have activities just finish and start as they come, or you can have the leads and lags between activity. A lead time is starting a task before the previous task is fully finished. A lag time is delaying the start of the next task before the next one starts. Another important term to understand is the baseline schedule. The baseline schedule is the approved plan. It's the contract schedule. It's what we said we were going to build at tender. It's what we signed a contract to deliver. This is the basis of how we're going to deliver the project, and it's going to be used to assess and track progress. So we're going to report on progress against our baseline, and it's going to be used to assess variation. So if there's a change the way we're working, change the completion date, we're always going to refer to the baseline schedule versus what we have currently. Another important concept to understand is schedule levels. So schedule levels refer to the level of detail in the schedule. We have level 1, which is the high level master schedule, which is what the client will be seeing. It's just very high level, showing key things like design, construction, commissioning, handover. Level 2 would be a package or area schedule where you've broken out, say construction, you've got it broken into earthworks, concrete works, structural works, and it's broken out into more detail. Level 3 is a target schedule where you break down, again, say excavation, into a couple of key activities with milestones. And this is where you sort of capture the interfaces between the different areas. Then below that, your level 4 to 6 schedules is the schedules the construction teams or the relevant disciplines use to plan out their work in detail. They might have a 2 to 6 month program, a 3-week look ahead, and then a daily plan. So a daily plan of exactly what's going to be done each day, which will roll up into a 3-week plan. So what are we getting done in the next 3 weeks? What's every single task we need to do? And this will be captured in your midterm program. But these all need to align with the level 3 schedule, the level 2 schedule, the level 1 schedule. So I like to think of scheduling into 2 broad categories of activities. We've got development and we've got implementation. So development is where we create the initial schedule. It's where we create our baseline schedule, our plan for how to deliver the work. Implementation is then when we put this plan into action. A lot of people refer to this as monitoring and control, but to me, that's wrong. We're not just monitoring and controlling a schedule. We actually need to put the plan into action. The schedule baseline is our Bible. It tells us what needs to happen and when. We need to take this plan and we need to follow it. And if things change, we need to change the plans. What happens so often on projects is people ignore implementation. They create this super detailed, amazing schedule, put a ton of effort into it. Then when it comes to delivery, they just ignore it. So that's why I like to think of it not so much as monitoring and controlling, but implementation, taking the plan and putting it into action. So development is creating a plan for how to deliver the project. Our plan is our project schedule. Tell us all the work we need to do, the start and finish date of all the activities, the durations and the linkages, what needs to happen before, what needs to happen after. So there's 6 steps to building a schedule. Step 1 is to identify all the activities. What is all the work we need to do to deliver the project? Step 2 is to sequence the activities. We take these activities, put them into a logical order. We then estimate their durations, develop the model. So put all this together, the tasks, the sequence, the durations. It gives us our schedule model, our Gantt chart. We then optimize and analyze this. Is it breaking any constraints? Are we running over our finish date? What do we have to change? And then We get feedback and input from our stakeholders to check that everyone's happy with it. It makes sense. It captures how we're going to deliver the project. And then we've got implementation. So building a plan and doing nothing with it is pointless. It's a waste of time, but it happens all the time in construction. People spend so much time planning and then they do nothing with their plans. The only value a plan has is when it's followed. So schedule implementation is putting the plan into action. So how do we put a plan into action? We need to understand and interpret the initial plan. We need to take our master project schedule and we need to work out what's going on. What do we actually have to deliver? We then take a chunk of this, our scope of works, what we need to deliver, and we develop a short range program. So depending on the type of project you're doing, this might be a 3-week look ahead. This might be a 3-month look ahead. We then focus on our enablers. What do we need to get ready? What do we need to have in place to deliver the project? We then manage our lead times. We look ahead far enough. How far ahead do we have to order materials? We get everything ready in time. We then track and monitor. We look at how much work we're getting done, what the plan's telling us, what do we need to change, and if things are deviating from the plan, we implement corrections. Don't worry, I'm going to cover all these steps in a lot more detail in just a second. So schedule development is how we build a schedule that complies with the project requirements, captures the construction methodology, optimizes the construction methodology, so it comes up with the best solution, both in terms of cost, time, safety, quality, factors in our constraints, so limited resources, access to site. It's easy to understand and follow, and it can be used as a tool to manage the construction work. So the schedule we develop has to tick all of these boxes. So the first step in this process, number one, is we need to identify all the activities. This is creating our activity and task list, all the tasks that need to be completed to complete the project. We do this with our work breakdown structure, which is our hierarchical decomposition of the project scope. We take the overall project scope, we break it down into component pieces. Now, our activity list is going to be a function of two things: the scope of the project, so the drawings and specifications, what we need to do, but also our methodology. So our methodology is an important factor to consider when we're creating our work breakdown structure. We're going to make important decisions around how to deliver the project, which will actually influence task list. For example, are we going to use precast concrete or are we going to do in situ concrete works? Can we get stuff fabricated off site? We're going to build it on site. We're going to break an area down into 4 separate areas and have 4 separate crews in it, or we're just going to have one big area. A lot of the steps we go through when we create our work breakdown structure are going to be driven by the methodology we choose. As an example, the work breakdown structure for a road project. So this is what we need to create for our project before we can begin building a schedule. A road project, we might break down into earthworks, structures and bridges, utilities, and roadworks. Under each of these tasks, we then break them down into another level of detail. For example, earthworks, we could break down into clearing and grubbing, bulk earthworks, drainage, and subgrade preparation. Our utilities might be broken down into services installations, street lighting, traffic signals, utility relocation. So each of these tasks then break down into another level of detail. Again, within the utility scope, we had street lighting. So street lighting, we could break down into the pits, conduits, and foundations, the lighting poles, the distribution boards, the power supply boards, and the circuits and luminaires. From this level, we can then create our list of work packages. Work packages are the tasks in the schedule. To create our actual work packages, we've taken the project and we've broken it down into 3 zones. So pits, conduits, and foundations. We've got zone A, zone B, zone C, zone D. We've done this for all the different tasks: pits, conduits, and foundations, lighting poles, distribution boards, and circuits and luminaires. Based on this, if we were turning this into a schedule, we would have a task in our schedules for pits, conduits, and foundations in zone B. We'd have a task in our schedule for the circuits and luminaires in zone C. So this is our work breakdown structure dictionary, our task list for the project. So when you're doing this, I just want to stress the point that methodology is an important input to creating your task list. For example, you might have a 200 meter cubed concrete slab. You could do this in 2 pours, or you could do this in 1 pour. Depends on whether you're going to add a construction joint or not, whether you're allowed to, whether you can get approval from your client. If you have 2 pours, obviously have to reflect that in the schedule. If you have 1 pour, your schedule will look different. So actually, how you choose to build it will impact your total task list. Again, As an example, let's build a really simple schedule for this concrete slab. So you can see this concrete slab here. We're going to break it down into a series of tasks and we're going to start entering it into a Gantt chart. So we've got this concrete slab. We can see it's a 100 mil thick concrete slab. There's a series of ground beams. Review the drawings and we look that you can see with the ground beams, there's no construction joints between the beams, which we can assume we can pour the whole thing at once. So I'm using a simple Gantt chart software for this. So the first thing we have to do, we have to identify the tasks. We'll break it down into initial and concrete. So we've got mobilization, bulk earthworks, and materials. So these are the 3 tasks that have to be done before we can start works. And then for concrete, so once these are done, we can actually start the concrete works. We've got detailed excavation. So this would be excavating for all the ground beams. We'd have formwork. So this is putting the formwork around the edge of the slab. We'd have steel fixing. Just call that formwork. Placement, steel fixing, concrete pour. Curing, you could show this as a task or a lag. We'll show it as a lag, so we'll add this later. Concrete pour, formwork, strip. And they are all the tasks in our schedule. Our work breakdown structure is really simple. So we've got this set of tasks under concrete and this set of tasks under initial. After we've defined all the work we need to do to complete the project, what we have to do next is to put them into sequence. Now, I understand that this happens iteratively. We go through, we find the tasks, we put them in order, we realize we missed some tasks, we go back, we do it. I understand it happens iteratively, but laying it out as a 6-step process is just an easy framework to think through it. So next, we're going to talk about how to sequence the tasks. So sequencing the task is capturing our methodology. It's putting the work in the order it needs to be done. What needs to be done before a task and what can be done after. This is referred to as the network schedule. You don't have any durations, just the tasks and linkages. We also want to introduce our leads and our lags. So for example, after we pour concrete, how long does it need to take to cure? These are our leads and lags. And we've already spoken about the different types of linkages. Our mandatory linkages, what has to be done a certain way, and our discretionary linkages, choices we're making about how to sequence tasks. Now, my really strong recommendation is when you do your first cut of the schedule, just focus on mandatory linkages. Big mistake I see people make is they do both at the same time and it gets really confusing. When you do your first cut of the schedule, keep it simple, just do the mandatory task linkages. Okay, so let's take from our example road project, the work breakdown structure we had in the last section. Let's break this down into a network schedule for the street lighting activities in one zone of the project. So we can start the street lighting works, the pits, conduits, and foundations once the earthworks are complete. So we've got a milestone in our schedule for earthworks completion. Because the foundations have a 5-day curing time for the concrete before we can start standing the poles, we have a 5-day lag before we can supply and install the street lighting poles. We then can also supply and install the distribution boards. And once these are done, once we've installed the poles, we've installed the distribution boards, we can start installing and terminating our cabling. And at the completion of this, we've got our street lighting in zone A complete. So that's the general methodology of how we're going to do the job. We have to do the pits, conduits, and foundations first. We have to wait for the concrete to cure. Then we do our poles, install our distribution boards, and then we can install our cabling. Okay, so for our concreting project, let's go through and do the same thing. So our initial tasks are going to have no predecessor in them. They're just going to be the start points of our schedule. So we'd have no predecessor. We'll just give it a fixed start date. So let's give it today's date, 12th of May, 20. Same with our earthworks and same with ordering our materials. These are all going to start on the same date. They're going to have no lag between them. What happens next? So the first thing we need to do is we need to do our detailed excavation. So for that to be done, we need to mobilize the site and we need to have done our detailed excavation. Remember, we're putting no durations in yet, so we're going to go through and fix up these durations in the next section. Then we can place our formwork once we've done the detailed excavation, and we can start the steel fixing at the same time. So steel fixing, formwork start at the same time. Once our steel fixing and formwork's done, we can place our concrete. So we need 7 and 8 complete to the concrete pour, and we then can strip our formwork once we've done that. Importantly, but when we pour our concrete, we have to wait for it to cure. So we have to wait we have to introduce a lag. So we've got a formwork strip, and we're going to introduce a 5-day lag to allow for the concrete curing. I think I've done that wrong. Sorry, it's that wrong task. So I make that concrete pour with a 5-day lag, and that 5-day lag you can see here, that is the concrete curing time. Once that's done, the tasks are complete. Okay, so we know the tasks, we know the order. The next thing we need to know is the duration of each task. We have to estimate from start to finish how long each task will take. Now, this is going to be a function of the activity itself, the nature of it, and the resources we apply to it. Remember at the start, we spoke about the difference between a production-based task, which is purely driven by resources and productivity, and a program-based task, which has some sort of fixed set duration. We also need to consider whether we're self-performing a task or whether we're subcontracting a task. That's going to impact how we go through the process and estimate the durations. We also need to consider the calendar. So the calendar is the days available to work. Are we working a 24-hour shift? We're doing night shift? Are we working Monday to Saturday? Or are we working Monday to Friday? Are there a ton of public holidays coming up? So on and so forth. So we need to consider available working days. Okay, so when we're estimating the duration of an activity and it's a production-based task, it depends on a quantum of work. So say we have 1,200 meters of trenching to do. We then need to know a productivity per shift. So for example, 40 meters per shift, which is going to be driven by the resourcing we allocate to the task and the task itself. So whether we're going to have 100, 1,000, or one crew. That's going to give us the total number of shifts that task is going to take. So if we have 1,200 meters of trenching, 40 meters per shift, we're going to take 30 shifts to finish the task. Now, if we're self-performing a task, so we're using our own labor, plant, and materials, we need to do a bottom-up estimate to determine how long the task will take, or we can use benchmark information from other projects. The key is we're using our own labor, plant, and resources, so we need to come up with the productivity rates. Now, on the other hand, we might be subcontracting out a task, which means engaging an external contractor to complete it for us. Subcontractors will have agreed upon programs in their contracts, which we can use activity durations in the agreed upon programs to estimate. Then we can independently check and verify this using a bottom-up estimate or a parametric estimate. But when we're subcontracting a task, we'll need to take the subcontractor's program of works and integrate it into our own. Now, when we did that calculation of 1,200 meters of trenching, 40 meters per shift, gives us 30 shifts. That's not the actual duration of the task. That's the number of shifts it will take. The schedule calendar is going to help us determine the start and finish date of the task. Are we working 6 days a week? Are we working 5 days a week? Public holidays, night shift, all these sorts of things captured by our schedule calendar. Okay, going back to our street lighting example. So we have civil self-perform work, so we're managing work ourselves, and electrical subcontractor doing the light poles, installing the distribution boards, and doing the cabling. Let's work out how long this task will take. Okay, so for our civil self-perform works, because we're self-performing the works, we need to do a bottom-up estimate. So we're looking at the working hours for the day. Say it's a 10-hour day. And we're allowing for 3 hours of non-productive time. We've got pre-start, we've got lunch breaks, we've got setup, pack up, these sorts of things. So we get really 7 hours a day when we're working. Like we know a crew from past project data can install 20 meters of conduit per hour. This equates, because we've got 7 productive hours per shift, this equates to 140 meters per shift. For our pit installation, a crew can do half a pit per hour. So it takes them 2 hours to install a pit. And for our foundations, again, they can do half a foundation per hour. It takes them 2 hours to do a foundation. So we can do 3.5 foundations per shift and 3.5 pits per shift. Now, we also know the total volumes of work. So based on the total volumes of work, we can come up with a total number of shifts. So we've got 25 shifts for the conduit installation based on 140 meters per shift, 40 shifts for the foundations, and 10 shifts for the pit. So this is just based on the total quantity of pits and foundations. And this gives us a total number of shifts for all these tasks. So we need 75 shifts of work to complete the civil works in Zone A. Okay, let's go back to our example, schedule the concrete foundation. So I'm not going to do quantity takeoffs and work this out, but this is how you'd have to do it. You'd have to say detail excavation, there's 100 meters cubed of soil to move. We can move 20 meters cubed per shift, so it'll take 5 shifts. That's the type of calculation you have to do. You do these calculations and then you enter the durations into the schedule. And since we've already put in the linkages, it'll fix the task. So formwork, we'll say there's like 100 meters squared of formwork, and then we're going to put 4 guys on it, and it'll take 3 shifts to do the edge boards. Steel fixing, there's 20 tons of steel. It's going to be 2 guys on it. It's going to take 4 shifts. So as we put in these numbers, you can start to see that our schedule is actually coming to life. So we've got the concrete pour, which concrete pour will take 1 day, and then the formwork strip will take 2 days. Based on this, we've actually created our schedule model. So we know the work's going to start on the 13th of May, and it's going to finish on the 4th of June. So once we've got our tasks, our sequence, our durations, we put all this together, we get our schedule model, our Gantt chart. These are our activities displayed against time, represented by a bar chart. They show the activities, the planned start and end dates, the activity durations, and the start and end dates of the overall project. So you can use the traditional way of doing it by hand, but the reality is in 2025, you're not going to be doing that. You're going to be using some sort of software tool to create your schedule model. It's really a couple of different tools we've got at our disposal. I'll categorize these based on what typically project engineers or construction people would use. And then you've got specialist software that planners and project scheduling professionals tend to use. So for project engineers, a lot we'd use Excel to do something like this. This might just be listing out your tasks and shading them to represent the bar charts of the Gantt chart. And we use this a lot for things like a 3-week look ahead or short range programs. Slightly more concept like a 6-week look ahead or a mid-range program. You might use something like Microsoft Project. I use Smartsheet because I just find it way easier to use than Microsoft Project. As a project scheduling professional though, you're probably going to be using something like Primavera P6, which would have your master project schedule, might have thousands of lines on it for a big project, or the same with Innate as another proper project scheduling tool. Okay, so once we've developed the model, once we've put that information into project or a similar tool, we've got our Gantt chart. The next thing we need to do is we need to optimize and analyze it. We need to look at the critical path. We need to work out if it's violating any constraints. So the key question we need to ask here, is the schedule going to meet the objectives of the project? Does it fulfill our requirements? So we need to ask questions like, are we going to meet a finish date? Are there any interim milestones we need to consider? What is the critical path? Which activities have float? Can we optimize resources? Are there ways to minimize and reduce risk? And overall, we're trying to come to the conclusion, is the schedule correct for our project? When we do this analysis, we're really going to be looking at the critical path and asking the question, is the critical path correct? Because at the end of the day, that is what is determining the duration of the project. That is what has to make sense and be correct. You can be wrong about some activities that have more float. Ultimately, it's not going to have much of an impact on the contract you sign with your client. The critical path's wrong. If you have incorrectly calculated how long the project will take, it can have big consequences. That's why when you're doing this analysis, you always want to first look at the critical path and ask yourself, does it make sense? Is it correct? Are the activity durations correct? So often when you look at a critical path of the project, there's something the schedule model is telling you, but you just know that the information it's giving you, the result it's giving you is wrong. It just doesn't make sense that in reality, this would be the critical path. The biggest issue tends to be that resource estimates are either conservative or too aggressive. That's what tends to be wrong. When you look at the critical path, you see it and you realize like this isn't actually what would delay the project. We'd add more crews to this task. So then when we're coming to the question of how do we optimize the schedule, there's really two principal things we can do. We can come up with a smarter way to do things, or we can spend more money and have risk. When we're talking about coming up with a smarter way to do things, we should do this for all activities. We should always be questioning ourselves and asking, is there a better way to perform the works? On the other hand, if we're talking about introducing risk and spending more money, we should only be applying that to critical path or near critical path tasks. Remember, the critical path is a calculation. On a year-long project, if a task has 10 days float, less than 10 days float, for all intents and purposes, it is on the critical path. Your schedule isn't going to be accurate to the day, so you can confidently say that this isn't on the critical path. If it has less than 10 days float and it's like a year-long project, again, it depends on the overall duration, proportionate to the level of float. Critical path, near critical path, in my opinion, the exact same thing. So as we spoke about when we were defining these scheduling terms, for these critical path or near critical path tasks, we can crash them, we can add resources to them that's going to increase our cost, or we can fast track them, we can overlap them, which introduces risk. Okay, so the important final step in developing a schedule is to get our stakeholders to review it. This is going to really tie into when we talk about implementing a schedule, but we don't want to just build a schedule in isolation. We want people to give us feedback. We want them to tell us what's wrong, what's right, review it, pick up errors we've made, basically get the whole team on board, get everyone to say, yes, this is the plan we're going to follow to deliver the project. The other way to think of a stakeholder review is just getting their buy-in to the plan. You want people to say, this is my plan. Yes, we can achieve it. Yes, we are happy with those dates. We're happy to meet them. A schedule is completely useless if nobody follows it. You need to ensure the plan is realistic, people understand it, and that people own it. They've given it their tick of approval, they've given their feedback into it, and they say they're willing to help achieve it. So up next, my favorite topic in project scheduling and the one everybody ignores, schedule implementation. Schedule implementation, put simply, is the process of turning our plans into action. We've spent schedule development building a schedule, creating it. The next thing we need to do is we need to turn that into a series of tasks that we perform to complete the project. Time and time again in my career, I've seen people put all this effort into building fancy schedules. They've spent hours working on them, they've workshopped them, they've done all this stuff. And then when it comes to actually delivering the project, as soon as it starts to get a little bit chaotic, they throw the schedule out, they put it in the drawer, they never look at it again, and then the project becomes a disaster. All that time they spent building the schedule, thinking through everything, suddenly becomes wasted. The core message is that planning without action is a form of procrastination. It's a complete waste of time. So if you're not even going to bother following the schedule, why did you spend all the time building it to begin with? So when we really dig deep and think about it, the only value a schedule has is when we follow it. Sure, it helps us to assess feasibility and cost, but the real value in a schedule is to help us deliver the project. It's pointless to develop a schedule if we're never going to implement it. So schedule implementation is all about putting the plan into action. It's about planning, coordinating, and delivering the works in accordance with the original plan. It's the process of executing the plan laid out in the master schedule. So we're going to take the high-level project schedule we developed, the master schedule. To implement it, we're going to break it down into clear, detailed actions. We're going to take the schedule and turn it into a list of tasks we need to complete, a to-do list. The goal is to make the schedule usable on site and turn it into a real-world set of actions, a to-do list that we simply follow to put the plan into action. Step one in this process is to understand the schedule. Now remember, on most projects, say we're in the construction team or the delivery team, we probably didn't deliver or develop the schedule. Sure, if we were lucky enough to work on tender and then move into construction, we would have. But a lot of the times we'll be thrown into a project and the first thing we need to actually do is to understand the schedule. So this will be reading, analyzing, and interpreting the schedule. When we do this, we want to be hypercritical. We want to understand everything in detail. And we also want to pick up all the mistakes and gaps. We'll typically get something like this, a whole lot of tasks with start and finish dates, red to represent the critical path. When we're onboarding ourselves onto a project, we need to understand the drawings, need to understand actually what we're building. But then the next step will be to look at how the drawings are mapped to the schedule, what we're building and how it relates to the plan. What's the methodology? What's the proposed resourcing? And we do that by analyzing the schedule. So the reason I said originally is that we want to be hypercritical when we do this is because schedules are always wrong. There's always things missing. There's always activity and linkages that are wrong. There's constraints or circumstances that have evolved that weren't there when the schedule was originally developed. There'll be detail missing and they'll have been changed. So when we're going through the schedule, we want to understand that this was the plan, but it won't exactly match reality. We need to be hypercritical and to understand what is potentially changing. Your job is to question everything, be hypercritical, understand the logic. Again, at the end of the day, your job is to achieve the project outcomes, the finish date in the contract, the time the project needs to be completed by, not to follow the schedule. Your job isn't to blindly follow the schedule, it's to understand it, understand the logic, and pick up any errors in it. The next step is that we want to decompose the schedule. We first understand it, then we decompose it. The master schedule that's developed will generally be relatively high level. It'll have a start and finish date for trenching, an access date, and a completion date based on high level productivities. When we're talking about implementing a schedule, we need to break it down into specific activities and tasks. These tasks will be more detailed than what was in the master schedule, and we're breaking it down into more detailed schedule levels. We capture this in a short range program. So a short range program is a highly detailed short-term schedule that we use to plan and coordinate all the minor activities that needed to facilitate the works. We could use something like an Excel document, a whiteboard, or even markups and staging plans. We use some sort of time slice method to do this. So we'll have a window of focus, it might be 3, 6, 9 weeks, depending on the project. And I'll talk about how exactly to determine this time slice you need to choose. And then we take the task in the master schedule, and we need to break them down into extensive detail into every minor thing that needs to happen to ensure that finish date for the task is achieved. Let me give you a quick example of what I'm talking about. So in the master schedule, we have basement excavation. That's a task with a start and finish date that probably won't capture any more information than that. We know the start date of the excavation and we know a planned finish date that the planner developed, probably based on quantities and assumed productivity rates. The 3-week look ahead, 6-week look ahead, depending on the time slice we choose, needs to capture every single activity that has to happen to ensure the basement excavation is completed by this date. So this means floating the machine to site, getting the surveyor to mark out all the depths of the excavation, setting up barricaded and temporary fencing around the excavation, excavating to the first design RL, then setting up shoring. So every task that has to happen will be captured in our 3-week or short range program. Now, when you're doing this, you're going to add a significant amount of detail. The only way you're going to know exactly what this detail is if you have a really solid understanding of the construction methodology, or more likely, you have access to people who understand what's involved in the works. You need to understand the methodology in detail, turn the tasks into subtasks that will all have their own dependencies and linkages. Now, you might not capture this in a formal Gantt chart or schedule. It might just be an Excel list. You need to understand the overall task is going to be broken down into 20 or 30 subtasks, and all these tasks relate to each other as well. Now, let me give you a really simple 3-week look ahead for some street lighting civil work. So we've got trenching and pit install for a certain range of the road, and then there's tasks allocated to this. For example, they need an excavation permit, they need service proving to identify in-ground services, and there's a planned start and finish date. We're also going to have quality assurance and testing. So testing the conduits, checking they're all installed correctly. We'll have another crew doing that. We'll have a crew doing the road crossing at John Street. Again, they need an excavation permit, and there's a planned start and finish date. And we're also going to be installing light poles on the bridge where they need a lifting permit. So we've mapped out the task, the permits we need, who's doing it, whether they need traffic management or a road closure, and the planned start and finish date. Now, in our master schedule, there might only be one line item in the schedule which says street lighting, civil works in zone 2. Our 3-week look ahead has broken this all down into detail. Now, the obvious question when we're doing this is, how do we work out what all of our subtasks are? Well, that comes down to pool planning. So pool planning is a tool where we ask ourselves before any task that's coming up, what is everything that needs to be in place to facilitate this task? And it helps us to transform our schedule into a to-do list. So let me give you an example. If we're talking about the master project schedule showing a certain concrete structure, so a planned concrete pour, let's think about everything that needs to be in place to facilitate this concrete pour. We need the excavation complete. We need the survey set out. We need any service penetrations within the slab installed. We need the materials to do the work. So we need temporary materials like formwork and consumables. We'll need the steel reinforcement. We'll need the concrete supply booked in. We'll need a subcontractor to complete the work, so our own internal labor if we're self-performing the task. We need safety documentation, and we'll need quality documentation. That is a list of things we need to get ready to complete the concrete pour on the fixed date. None of this will be in the master schedule. The master schedule will just show the concrete pour. Now, so before I mentioned a 3-week look ahead as an example of a short range program, but I also made the comment that the time slice you choose for your short range programs depends a lot on the task. Now, all these different activities, ordering the materials, getting the subcontractor onboarded, all these things take time. So this leads to the point of how long should your short range program or your detailed to-do list be, and it really depends on how long this stuff takes to get ready. Depending on the type of project, it might be really quick. If it's a more complicated project where you've got longer lead times for materials, you might have to be looking 3 or 4 months ahead to ensure things stay on track. So this is the idea of activity lead time. So activity lead times are basically just the time it takes to organize everything before we do the work. We need to consider, for example, the materials we need for the concrete foundation. We'll need steel reinforcement, so we need to allow for time to get it fabricated. We need to allow for time for the Rio supplier to get shop drawings and steel reinforcement. We need to get those reviewed and approved. We need to actually award a contract to them to supply the materials, which means we need multiple quotes and to go through some form of procurement process. Okay, so let's imagine we have a concrete pour on the 28th of June. For this concrete pour, amongst the 20 other things we're going to need ready, we also need the steel reinforcement on site, which means if there's a 3-week lead time for the steel reinforcement, we need to award the contract and place the order by the 7th of June. If we need to allow 4 weeks to get quotes, to negotiate rates, to get internals approvals, to sign off the contract, we need our quotes back by the 7th of May. So 1 month before that. If we need 4 weeks to review drawings, do our quantity takeoffs, prepare our tender packages, that means we need IFC drawings that tell us what steel reinforcement we need on the 7th. So that's just one example of one chain, which is the procurement. So you can begin to see how far ahead you need to be planning to ensure a concrete pour on the 28th of June isn't delayed. Now, depending on the project, these dates will change, but for the example of the concrete pour, you need to be thinking about a June concrete pour as far back in April. Now, I've worked on solar farms where we've been ordering transformers that have a 70-week lead time. So the core message I'm trying to give you here is you need to be really planning far ahead to be allowing enough time for all this stuff to happen. Again, the core message, think about what needs to be in place for the activity to happen and how far in advance you need to be getting that stuff ready. So the core process I've spoken about here is to decompose the master schedule into a series of subtasks. You do this by identifying all of the tasks that need to be completed for the activity in the master project schedule to be completed. And to do this effectively, to make sure the master schedule isn't delayed, you need to understand how long this stuff takes to get ready by understanding activity lead times. So at the end of the day, schedule implementation is where scheduling meets time management. So much of schedule implementation is just being organized, preventing roadblocks before they occur, thinking through what has to be in place for this to happen, constantly asking yourself the question, have I identified everything? Is it ready? Is it going to be ready on time? Effectively, what you're doing in this step is you're taking your schedule, you're transforming it into a to-do list. This might be done in Microsoft Planner that I've always found with schedule implementation, you don't really want a complicated Gantt chart. You just want an Excel document, a to-do list, a whiteboard, something really simple that the team can see and everyone can be working back from. Okay, so we've taken the plan and we've worked out how to put it into action. The next question comes up is how do we know we're sticking to the plan? So that's why it's the next section. We're going to talk about monitoring and controlling the schedule. How do you ensure you're staying on track? Now, there's a lot of different ways people express the monitoring control process. I like to think it of asking a question, how do we ensure we are following the plan? Schedule development, we built a plan. Schedule implementation, we took that plan, we turned it into a to-do list. We started working through all the actions to put the plan into action. Monitoring and controlling is then the process of checking that what we're doing matches the original plan. And if it doesn't, updating the schedule and addressing variances. Now, when we built the schedule, there were assumptions, there were guesses, there were unknown and unknowable things, and that's just the reality of construction projects. Every single construction project is different. Every project is unique. When we're planning the projects, there are things we cannot foresee. There's changes that will happen. There's unknown and unknowable things that will happen. So by monitoring and controlling the schedule, progress tracking, we need to keep the plan relevant and useful. It'll help with managing our stakeholders, and it helps us to identify issues and deviances early. So fundamentally, monitoring and controlling the schedule means tracking progress, comparing how much work we're doing versus what our baseline plan is, understanding deviations from this plan, so understanding delays, and then when there are delays, applying treatments to them. Effectively, monitoring and controlling the schedule helps us to ensure the plan is still useful and relevant. It helps to ensure it still remains a useful planning and coordination tool. It helps us to then plan activities, book resources, and make informed decisions about cost, time, and scope. And if the information in the schedule is wrong, if it's not updated, then it can't be a useful tool that helps us do this. Now, let me work through an overly simple example, but it's here to illustrate the point of why you want to keep the schedule relevant and useful. Say cable installation begins after the conduits are complete. The conduit installation is currently at 10% complete, but it should be at 90% complete. Looking at our schedule, our cable install is planned to start next week, but cable procurement has been delayed and everyone's stressed because the cable is not going to be here in time to start installing it. We've got an option to pay for an expedited delivery. The question is, should we do it? Well, looking at these numbers, obviously not, because you can see the conduit install is only at 10% complete, even if it was meant to be at 90% complete. If we're updating our progress, tracking our numbers, we can clearly see the cable installation activity that's planned to start next week isn't going to happen because the conduit installation is so far behind. So the question, should we pay for an expedited delivery? Obviously not. Okay, so the schedule helps us to make informed decisions around our progress and planning and coordinating the works, but it also helps us to manage our stakeholders. The schedules used to inform our stakeholders of progress becomes a source of truth they can look at to see where everything's up to. Often it's also a contractual requirement to maintain a schedule written into the contract we have with our client that we'll need to provide them fortnightly or monthly progress updates. The schedule is how we capture realistic information, how far we're through different tasks like procurement or what percentage we're complete we're on piling. Now, the final reason we should monitor and control our schedule and keep it relevant is it gives us a way to look into the future. It's a lead indicator. It helps us to know if something's going to go wrong before it goes wrong. This is the opposite to a lag indicator where something goes wrong and retrospectively we can look at it. So a lead indicator is a way of seeing into the future and preventing mistakes before they happen. As an example, say we know our piling is 10% complete at the end of week 1 and our schedule has a 4-week program for piling. It's a critical path activity. So any delays to the piling will delay project completion. What should we do? Well, clearly we're going to delay project completion because we're 10% complete and we should be around 25% complete. We could look at options to do weekend work. We could look at options to do night shift. We could look at options to bring in another piling rig. The only reason we know that is because we understand the schedule. We know it's a critical path task. We know it's 10% complete at the end of week 1 rather than 25% complete because we've tracked progress and we've maintained our schedule. Okay, so the first part of scheduling, monitoring, and controlling is progress tracking. Progress tracking is basically just determining the percentage complete of each task in our schedule. And it's a really simple process. We first need to understand the activity we're tracking. We need to set up a progress tracker, and then we need to monitor the activity and record the actual quantities of work complete. Okay, so first when I say we need to understand the activity we're tracking, we really want to understand whether it's a production-driven task or a milestone-driven task. Production-driven task means the activity can be represented by a baseline quantity. The progress for the task is the quantity of work complete. For example, if we know we need to do 10 kilometers of trenching and we've done 500 meters of trenching, we've done 5% of the work. For example, piling, that's another production-driven task where the percentage complete is just represented by the number of piles completed versus the total numbers of piles. A milestone-driven task, on the other hand, is an activity that is a group of different sub-activities where there's no consistent metric we can use to track them. Classic example of this would be procurement. You're not going to track the number of words of a scope of works that someone's written. It's just a series of different tasks grouped together. So we might have writing a scope of works, issuing the tender, getting quotes, contract award. You track these by giving fair representations of the work to each of the sub-activities and tracking whether that sub-activity is completed. Okay, So if we want to set up a progress tracker for a production-driven task, we want to determine the activity to be tracked. We want to determine the total quantity of that work from the design. So for example, we're tracking trenching. We've got 10 kilometers of trenching. Then we want to determine the start and finish date for the activity to give us a daily quantity or weekly quantity we need to be completing. Okay, let's do an example for street lighting civil works. We want to track the percentage complete of the street lighting civil works in an area. However, we run into the challenge where we've got 3 different tasks for tracking. We've got pit installation, conduit installation, and foundations. The metric we want to track is linear meters of conduit installed because that's the biggest task. We could say, for example, we could have tracked the overall task by the number of pits or the number of foundations, but in this sense, made the most sense to track by linear meters of conduit, which means we have to represent pit installation as equivalent to 20 meters of conduit. This would be done based on, say, if a pit takes 4 hours to install and 20 meters of conduit also takes 4 hours. We could just baseline it like this. Again, we're saying a foundation is the equivalent of 60 meters of conduit. Okay, so let's come up with a total quantity of work we need to track in zone A for the pits, conduits, and foundations. So conduit install, we've got 3,500 linear meters. Pits, we're saying we've got 35 pits, which is the equivalent to 1,050 meters of conduit. And we've got 140 foundations, which is the equivalent to 2,800 meters of conduit, using that equivalence we came up with in the previous section. Okay, the next thing we need to do is we need to come up with our daily targets. How much work do we have to do per shift, per day, or you could do this weekly or monthly depending on the project. For example, pits, conduits, and foundations in Zone A, we've got a design quantity of 7,350 meters with 75 shifts, we can come up with a daily target of 98 meters per day. We can do this for all the activities in our schedule. We come up with a planned daily target. Then all we do to track progress is we set up an Excel template similar to this, where we've got for the activity, we've got our planned target each day, our planned total, so our cumulative total, our actual what we actually got each day, our cumulative actual, and then the quantity remaining. So for example, on the 1st of October, we plan to do 100 meters. Our cumulative total is 100 meters because we've only done 1 day of work, but we actually got 98 meters. The next day, we plan to do 100 meters. Our planned total is now 200 meters because we should have done 2 days of work. Our actual quantity was 121 meters. So our cumulative total is 219 meters. So you can see that each day we track how much work we did versus how much we planned, which gives us the cumulative total and also a quantity remaining. Okay, so if we want to track a milestone-driven task, now remember this is an activity which is a set of sub-activities with no consistent quantity or metric we can track. We need to determine the milestones that break down the task. We need to set up some sort of credit system, and then we need to monitor against this credit system. Again, this isn't going to be as objective and scientific as a production-based task, but it's still a useful way of tracking activities that can't be represented as a single quantity of work. So for example, if we're talking about procurement, we might have the following milestones to represent a task. The tender package is ready and prepared by a team. The tender has been issued to the market. We've received quotes back. We've awarded a contract, and then they've mobilized the site. So the activity of procuring a subcontractor is broken down into 5 different tasks. We then apply a percentage to each of these tasks that would best match the reality of how much effort or time that task would plan to take as a representation of the overall task. For example, the tender package being ready, we represent as 10% complete. The tender issued and sent out to subcontractors, we represent as 20% complete. The quotes received back from subcontractors, we say we're 50% complete on that task. The contract has then been awarded, signed, and negotiated. We say we're 75% complete. The subcontractor on site, mobilized, ready to begin works is the 100% complete milestone. Basically, when we're setting up a credit system, we just want to come up with some realistic, logical weighting of tasks that represents the real level of effort or duration. It takes 1 week to prepare a tender, 2 weeks to get the quotes. The activity of getting the quotes should be worth 2 times the preparation of the tender. It's really simple. It's just how long will that task we're planning for it to take, how much effort does it take, and just weighting the sub-activities appropriately. Then simply based on what step we're up to in the overall process, we can make a pretty accurate estimate of the overall task completion. Again, it's more subjective, less scientific than a production-based task, but it's the best way we have to do it. The better the metric we have, the better or more accurately we've broken down the tasks, the better the actual information in our project schedule is going to be. Just to summarize, where are we up to? In terms of tracking progress, we've understood the task. We understand if it's production driven or milestone driven. We've set up a progress tracker, a way of capturing the raw work performance data, and we're monitoring our tasks. Every day we're recording how much work's getting done. We're comparing this to our planned targets. So what we've tracked so far is our raw work performance data, simply how much work we're getting done. We can then calculate a series of metrics with this that help us to better understand how we're tracking. So the first one is percentage complete, which is simply the work we've completed divided by the total quantity of work we need to do. We can also calculate our production, which is the quantity we've completed divided by the time elapsed, which allows us to calculate a daily or weekly production, what we're actually hitting. We can calculate our schedule variance. So schedule variance is the difference between how much work we've done minus how much work we plan to do. If we get a positive schedule variance, it means we're ahead of schedule. If we get a negative schedule variance, it means we're behind schedule. Similarly, we can calculate our schedule performance index. So schedule performance index is the ratio of earned value, how much work we've actually done divided by planned value, how much work we plan to get done. We can also calculate our estimated completion date. So estimated completion date is elapsed time, so how far we are into the task currently, plus the ratio of the work remaining divided by our actual production rate. So basically, we're 5 days into the task, we've got 100 meters left to do, and we're doing 20 meters a day, then we're going to need another 5 days to finish. That gives us our estimated completion date. And let's work through an example. Say we're installing inverters on a solar farm. We've got 100 inverters to install. Our plan is to hit 4 per day, which gives us an estimated duration of 25 days. As an example, we're at day 10, and so far we've installed 25 inverters. So at day 10 of the task, let's calculate all our key metrics. So percentage complete, well, we've done 25 inverters, we've got 100, so we're 25% complete. Our actual production, we've done 25 inverters over 10 days, so our actual production is 2.5 inverters per day. Our schedule variance, well, we've done 25, we should have done 40, which after 10 days at 4 per day, that's our plan value if we'd planned to do 4 per day. So we're 15 inverters behind schedule. Our schedule performance index is the ratio of what we've done versus where we should be. So we're at 0.625, which means we're doing 62.5% of the work we should have been doing. And our estimated completion date is day 10, where we're up to now, our elapsed time, plus the ratio of the remaining work we have to do by our actual production rate. So we've got 75 inverters left, and we're doing 2.5 per day. It's going to give us 30, which means our forecast completion date is day 40. As you can see, by calculating these metrics, we've given context to our raw data. The next thing we need to understand is that this information is only useful if we act on it. So it's great we've calculated these metrics, but what are we actually going to do about them? So this leads us to the idea of a treatment. The only value information has if we act on it. If not, it's a waste of time. The same with planning without action. It's just a form of procrastination. So what do we do if the works are delayed? What do we do if we calculate our metrics and we see that we're behind schedule or we need to apply a treatment? Treatments is all about understanding what can we do about the delay and choosing the optimal solution to the problem. So when we're choosing a treatment, we need to understand first, so what type of activity is being delayed. We need to then identify the root cause of delay and explore options we have and correctly implement them. Okay, so there's fundamentally 2 types of activities that can be delayed. A critical path activity, which is an activity that will delay project completion. And importantly, we also want to talk about near critical path activities. So these would be activities that have less than 10 days float or whatever a reasonable reference point is, depending on the type of project you have. If it's a short project, it'll be plus or minus 1 or 2 days of float. It's a really, really long project. It might be activities that have within 30 or 40 days of float. The idea here is your critical path is a calculation, so it's never going to be 100% accurate. The other type of activity that can be delayed is a non-critical path task. These are activities that have a significant amount of float that we can delay without impacting the project finish date. Then we need to understand the specific root cause of the delay. Is it a resource constraint? Can we not get enough people or machines to do the task? Is it planning or scheduling issues? Have we poorly planned? Is our initial plan wrong? So we have project management issues. Are we not managing or coordinating the works properly? So we have technical challenges. There's complex design or construction methodologies or design constraints that we need to address. Are there external factors or are stakeholder approvers holding us up? We really need to dig deep to understand what actually is holding the activity back. What is changed from when we prepared our baseline schedule? So we've understood whether it's a critical or non-critical task that's being delayed, and we understand the root cause of the delay. What can we then do about this delay? Well, there's fundamentally two things we can do about a delay. We can optimize and improve, which is improving the systems and performance, how we're organizing the works, coming up with better design solutions, all these sorts of things. Or we can do both, or we can add cost and risk to make sure it's done faster. This means crashing, where we add additional resources. We go from 2 crews to 3 crews, or we fast track tasks. So originally we might have planned to finish one task and then start the next one. Maybe we can start the following task with a 50% overlap. Now, for optimizing and improving the task, we should do this for all activities. We should constantly be asking, how do we do it better, faster, cheaper, with a better design? We should always be doing that. That would apply to both critical and non-critical tasks. But if we're talking about crashing or fast tracking activity, adding cost and risk, we should only do that with critical path or near critical path tasks. But at the end of the day, we're going to spend more money and add additional risk. And the only reason we would benefit from doing that is if it's a critical path task. If we can delay an activity and it doesn't impact the finish date, then we shouldn't be spending money or adding risk to it faster. We should only be doing that for critical tasks. The fundamental reason most schedules fail is because they're disconnected from the way projects are actually delivered. Here are 10 traps to avoid so your schedules reflect reality and to get ahead of 90% of project schedulers. I'm going to break these 10 traps into 4 sections: planning mistakes, logic mistakes, communication issues, and monitoring and adaptation issues. Planning mistakes are mistakes you make while you're setting up the initial schedule. And the first one is being precisely wrong rather than roughly correct. It's trying to build a highly detailed schedule in week 1 when you don't have any information about how the job will be built. It wastes tons of time on tasks that will change, and it creates a false sense of precision that just is not based in reality. So when you're first creating your schedule, start high level and then progressively add detail as you get better information. Start high level, get the job duration and overall methodology roughly correct, and then add detail when it becomes available. Mistake number 2 is blindly copying other projects. Every project is different. Every project is unique. Yes, templates can be recycled, but other projects should only be relied on with caution. I was working on a solar farm and I remember looking at the schedule and trying to understand why a specific activity was being rushed so aggressively and why it was coming up as holding up the entire schedule. And it was because we'd copied the template from another project that had a specific requirement in it for our development approval. We needed to put up the external fencing and landscaping, which wasn't applicable on the project we were working on. So we could see that the landscaping was holding up the entire construction of the panel system. It made no sense until we realized that the planner had simply copied a template from another project. So yes, you can recycle templates, you can use other projects, but you need to fundamentally understand how the project's going to be built and the project specifics and constraints. Because if you're just copying other projects, they might have unique requirements that aren't reflected in our project. The next mistake, which always confuses and overcomplicates things, is adding discretionary linkages too early in the planning process. This is when we're creating our first cut of the schedule during the planning phase and we add in a ton of non-contractual or preference-based linkages that don't match the hard logic of how the project has to be delivered. It extends the duration artificially, it adds confusion, and it'll make optimizing the schedule much more challenging. So when you're first building your schedule, focus on the hard physical dependencies, the actual construction methodology, what you have to do to build the job, then add in things like resourcing or other issues you want to capture in the schedule, preferences on how to build it, how to optimize for cost. Add this in as a later optimizing stage of building the schedule. And the final planning mistake is not properly linking procurement and design. People focus way too much on construction. They get into the details. But to build anything, you need drawings and you need materials and subcontractors. So failing to properly capture the durations of these tasks, the dependencies of these tasks, will lead to a schedule that has a very detailed construction phase, but everything that happens before it being completely wrong. Okay, so those are the mistakes people make during the planning phase. What about logic and data issues? These are issues with how the schedule is fundamentally structured and set up to track progress during construction. So the biggest logic mistake I see is people ignoring the logic and the methodology of the project. The schedule has to reflect the reality. It has to reflect how the project is actually going to be built. If for whatever reason, an activity can't start before your client's not giving you access, that has to be in the schedule. That is the thing that's driving the start date to that task. The schedule has to reflect reality. So many times you look at a schedule and it just doesn't actually reflect the way the work is being done. So you always have to be asking yourself the question, is this what's actually holding up the task? Is this what the task is actually dependent on? Again, it's all about being critical of the schedule and ensuring that the plan reflects reality. The next mistake I see people make is similar to the earlier one I had, which was about being precisely wrong rather than roughly correct, which is obsessing too much over the numbers rather than what they mean. People get way too fixated on percentages complete, dates, floats, the critical part, without really understanding what they represent and the sequence of the overall project and how they all fit together. It's being, again, too precise rather than roughly correct. It gives you a false sense of control. For example, a task might be marked as 90% complete, but that final 10% complete of the task might be some sort of defect that has a 6-month lead time on the materials we need to fix it. If you looked at the schedule and you didn't understand how that 90% complete was made up of, and that we were actually looking at a 6-month delay to rectifying a defect we need to have closed out before practical completion, then you're completely missing the point. Fundamentally, you still need to have a firm grasp of how the job's actually being built, the methodology, how the data is being captured, and what it actually means. You have to understand the methodology. The next mistakes I want to talk about are communication issues. These are mistakes that happen when planners and the construction teams are out of sync. The big one I see here is a disconnection between planners and construction. This happens when the schedules are created in isolation without input from the people managing and delivering the project. The sequence doesn't match the real world site conditions, and the team, therefore, don't look at the schedule, they don't use it as a planning tool, and they don't see it as their plan, so they don't have ownership over the outcomes. Fix to this is really simple. If you're the planner, you need to involve the people doing the work. They understand it better than you, and you want them to have ownership over it. You need to get them involved in the planning process. You need to work out a way to make it their schedule. The next mistake I see is people focus on schedule development and schedule tracking, monitoring, and controlling, but they ignore the fundamental step of implementation. If you create a schedule and don't implement it, as I've said before, it's a waste of time. You need to work out a way to take the plan that exists in paper and turn it into a to-do list. You need to work out how to bridge the gap between scheduling as a project management tool and time management and to-do lists. You need to work out a way that people can take the schedule, turn it into a set of actions, and then follow up on these actions. This is where scheduling and time management and organization are highly interrelated. And the final category of mistakes I see people making all the time is monitoring and adaptation. You need to adjust the plan when conditions change. A big mistake I see people making here is they treat the schedule as a Bible rather than a guide. Again, they follow the schedule blindly even when the conditions on site change. becomes a tool that people use to blame when things go wrong, rather than seeing it as a guide and understanding it might be incorrect, there might be issues with it, but you need to take ownership of it, understand what mistakes are in the schedule, understand the way the job actually has to be built, because fundamentally you're there to meet the finished dates, not to follow the schedule. And finally, people fail to update and maintain and reforecast the schedule. They treat the schedule, they develop it as a set and forget strategy. They build the schedule, they save it on their desktop, they never look at it again, and then they go and make all the mistakes that they identified in the schedule as issues that were going to come up on the project. Again, you need to constantly be referring to, maintaining, and updating the schedule so it remains a useful tool to plan and coordinate the project.